Hello, I'm Hongyan Zhang from Karlsruhe Institute of Technology. I'm going to present a brief overview of our recent work titled Aging Resilience and Fault Tolerance in Runtime Reconfigurable Architectures, in which the feature of reconfiguration and the homogeneous structure of FPGAs are exploited to mitigate aging and tolerate faults. The co-authors of the paper are Lars Bauer from Karlsruhe Institute of Technology, Michael Kochter, Erich Schneider, and Hans-Joachim Wunderlich from University of Stuttgart, and Jörg Henkel from Karlsruhe Institute of Technology. This work is supported by the German funding agency DFG under the Priority Program 1500, Dependable Embedded Systems. First, let me introduce runtime reconfigurable architectures. The most important feature of runtime reconfigurable architecture is the ability to instantiate hardware accelerators in runtime, which is called runtime reconfiguration. This slide shows a common structure of runtime reconfigurable architectures. A general-purpose processor is connected to several reconfigurable regions over a communication infrastructure. The reconfigurable regions are usually implemented with FPGAs. In runtime, depending on the application requirements, extra hardware accelerators can be loaded into the reconfigurable fabric to speed up the application execution. This kind of architecture provides the high computation efficiency with hardware accelerators and high flexibility with runtime reconfiguration. As the semiconductor technology advances, the FPGA devices are becoming more and more prone to various aging effects, which degrade the transistor performance and may eventually lead to faults in the circuit. This paper addresses the reliability issues in the FPGAs from two aspects. First, the device should fail as late as possible. Second, if a part of the device fails, the system should be able to avoid the faulty part and continue operating and therefore achieve graceful degradation. These are achieved by accelerator diversification during synthesis time and stress balancing during runtime. During synthesis time, we create multiple placement configurations for each accelerator. These configurations are diversified in terms of CLB usage on the FPGA. They guarantee that whenever a CLB in the FPGA is detected faulty, we can always find an alternative configuration of the accelerator that do not require that faulty CLB. In this way, accelerators can still provide correct computation even in the presence of faults. The execution of accelerators induces stress in the reconfigurable fabric, which leads to the aging of the transistors. By utilizing power estimation tools, we can estimate the stress each accelerator configuration will induce in the FPGA. For example, the number of toggles experienced by the transistors when an accelerator is executing. We also perform online monitoring, which keeps track of the accelerator execution history in the reconfigurable fabric. Based on the online monitoring and offline stress estimation, the runtime system decides which accelerator configuration should be placed at which locations on the FPGA such that the induced stress is uniformly distributed over all CLBs. In this way, the peak stress of transistors, which causes earlier failure of the FPGA, is reduced, and the lifetime of the system is thus prolonged. Let's look at an illustrative example of accelerator diversification. A1 is a configuration of an accelerator that uses 9 CLBs in a 3x3 region. If one of the used CLBs is detected faulty, this configuration will produce incorrect outputs. In order to avoid the faulty CLB, we prepare alternative configurations like A2 to A4 with additional placement constraints during place and route. By using alternative configurations that do not require faulty CLBs, we can tolerate faults at different locations. This slide illustrates the basic idea of stress balancing. During runtime, the application requests to configure accelerators to speed up its computational kernels. At this point, the runtime system has to decide into which region an accelerator should be configured. To minimize the peak CLB stress in the reconfigurable fabric, the CLB stress from the accelerators needs to be distributed evenly. To achieve this, we propose a heuristic that follows these two rules. First, we maximize utilization of under-stressed CLBs within one region. Say the stress should be evenly distributed among different CLBs within one region. We call it intra-region stress distribution. Second, we want to avoid placing high-stress accelerators into already highly stressed regions. Say the stress should be evenly distributed among different regions, which is inter-region stress distribution. We performed experiments using an H.264 video encoder as the target application. It consists of 9 distinct accelerators. This table shows the timing impact on the accelerators after we applied accelerator diversification to tolerate any single CLB faults in one region. The maximum system frequency is limited by the accelerator with the longest critical path. In this case, the point filter, which runs at 89 MHz. Overall, the timing cost of accelerator diversification on the whole system is 9%. We injected random CLB faults into the system to investigate the system behavior in comparison to state-of-the-art stress balancing methods. The upper chart shows the system performance in the presence of faults. With accelerator diversification, our system is able to avoid faults with alternative configurations, which minimizes the impact of faults on the utilization of accelerators. Therefore, our system can deliver sustained higher performance than other systems that do not have diversified configurations. The lower chart shows the maximum transistor toggle rate in the system in the presence of faults. Although our system has a higher level of resource utilization due to fault tolerance, it exhibits lower peak stress and thus longer system lifetime than other state-of-the-art stress balancing methods. Thank you for watching this video.